Hydraulic systems achieve incredible power density by relying on Pascal's law. This physical principle dictates that a pressure change applied to a confined fluid is transmitted as a uniform pressure in all directions, allowing highly compact machines to generate massive amounts of force. But calculating exactly how that fluid travels from a pump to an actuator is notoriously difficult. If you want to find the current moving through an electrical resistor, you use Ohm's law, a single, elegant equation. Fluid power offers no such simplicity. There is no single mathematical law that describes the hydraulic resistance of a passage. Instead, resistance is dictated by the microscopic internal geometry of the hardware and the precise physical state of the fluid itself at any given microsecond. The central challenge for engineers is to predict and control this highly reactive fluid behavior. If the internal flow is not managed accurately, the resulting pressure spikes and internal friction will tear the system apart from the inside out. Engineering a reliable hydraulic circuit depends on the explicit management of the transition between highly ordered and completely chaotic states of fluid motion. To map that transition, engineers rely on the Reynolds number. This is a fundamental, dimensionless mathematical ratio used to categorize all fluid behavior inside a conduit. It represents the battle between inertial forces pushing forward and viscous forces resisting movement. Below 2000, the system achieves laminar flow, smooth, parallel layers of fluid. Velocity is lowest at the pipe walls due to friction, peaking in the center. This orderly movement is the ideal state for transmitting hydraulic pressure. It produces the absolute minimum amount of internal frictional resistance, keeping the machine efficient. But push the fluid velocity higher, and inertia begins to dominate the fluid's viscosity. The smooth layers collapse into turbulent flow, a chaotic state defined by erratic, eddy-like paths of fluid particles slamming into the conduit walls. Crossing that Reynolds number threshold of 2000 reconfigures the underlying physics of the machine, turning smooth power transmission into chaotic resistance. To maintain that laminar stability, engineers calculate exact pressure drops using the Hagen-Poiseuille law, a mathematical model mapping fluid friction. The problem is that this equation assumes an ideal, perfectly circular tube. Real-world hydraulic components, with their intersecting valves and moving actuators, require highly specific geometric adaptations of this math. This diagram from standard hydraulic engineering references illustrates the specific challenge of calculating flow through an annulus. An annulus is the ring-shaped gap between a moving circular shaft, like a piston rod, and its stationary cylindrical housing seal. The critical variable here is E, representing eccentricity. This measures the exact degree to which the internal shaft is sitting off-center. Even microscopic shifts in eccentricity drastically alter the hydraulic resistance, leading to massive variations in leakage flow. The mechanical stakes are severe. In the extreme case, to actually touch the cylinder wall, the resulting flow through the widened gap is 2.5 times higher than if the shaft remained perfectly concentric. Because the actual eccentricity is often unknown during operation, engineers have to compute a theoretical hydraulic diameter for these non-circular spaces, just to establish strict radial clearance limits. Tiny geometric deviations rapidly compound into massive fluid leakage. To prevent a hydraulic seal from failing under its own internal flow rates, high-precision machining becomes an absolute mathematical necessity. But precision machining cannot prevent turbulence entirely. When system constraints force the fluid velocity past the laminar limit, the physical consequences are immediate. This chart plots flow rate against pressure drop. The dashed line, labeled slope equals 64, shows the linear relationship expected during ideal laminar flow. But as velocity increases, the actual data, the solid line, breaks away, arcing into a severe exponential surge in pressure drop. That exponential curve represents the exact mathematical penalty of turbulence. It is a total breakdown of efficient energy transfer. As the fluid loses its parallel structure, the random chaotic fluctuations of fluid particles slamming into each other act as severe internal physical resistance. The laws of thermodynamics dictate that this lost kinetic energy cannot simply vanish. Instead, the intense friction directly converts that energy into severe thermal heat within the fluid itself. In this way, turbulent flow acts as a continuous parasitic drain on the machine. It simultaneously saps mechanical power away from the actuators while generating heat that actively degrades the fluid's own viscosity, making the whole system less efficient over time. How does a complete hydraulic circuit survive when its internal physics are constantly fighting the machinery? The answer lies in macro-level system architecture. Engineers deliberately design the primary fluid conduits, the long stretches of piping that connect the major components, with notably large cross-sectional areas. This specific geometric sizing is calculated to drive the overall fluid velocity down. By slowing the fluid in these main arteries, the system intentionally forces the Reynolds number below 2000, maintaining laminar stability for as long as possible. But this stability is strictly temporary. Turbulence is completely unavoidable at the complex intersections of valves and actuators, where high-velocity jets and boundary layer dynamics create intense friction. Because these internal choke points are constantly generating heat, dedicated heat exchangers, components specifically designed to cool the fluid, must be integrated directly into the circuit. A functional hydraulic circuit is ultimately a strict thermodynamic balancing act. It requires sizing components to maximize laminar efficiency while simultaneously bleeding off the thermal penalty from those mandatory turbulent zones. There is one final hidden variable that destroys hydraulic systems faster than heat or extreme pressure: solid matter. Statistically, fluid contamination accounts for up to 70% of all hydraulic system failures. When solid particulate enters the system, turbulent eddies violently suspend the microscopic debris. The chaotic fluid dynamics turn the oil into liquid sandpaper, an abrasive mixture that permanently scores and degrades precision-machined valves. The operational response to this threat is strict cleanliness during initial assembly, combined with the integration of high-pressure inline filters designed to extract solid particulate long before it hits a turbulent zone. In the field of fluid power, clean fluid and system reliability are functionally synonymous terms. A successful hydraulic system does not attempt to eliminate the raw physics of fluid dynamics. Rather, it is a highly complex, precisely calculated architecture built explicitly to survive them.
In this session, Module CAT 017 covers advanced circuit design. Don't forget to like and subscribe to stay updated with our latest tutorials.